Hello students, Dr. T is here. Welcome back in today's class, which we're going to explore what atoms are, how scientists discover them, and how these tiny particles explain the structure and the behavior of all matter around us. So let's begin with one of the most important discoveries in chemistry, the electron. In the late 1800s, Thomson used a device called a cathode ray tube, which is basically a glass tube with the most of the air removed. And when he applied electricity, he noticed a beam traveling from the negative end to the positive end of the tube. So he realized these beams was made of tiny particles. They moved in straight lines, they behaved the same no matter what material he used, and they carried a negative charge. This was the first evidence that atoms contain smaller particles. Thomson had discovered the electron. And he didn't stop here. He used electric and magnetic fields to bend the beams and measure how strongly it responds. From this, he calculated the charge-to-mass ratio of the electron. This was a groundbreaking. Scientists now knew electrons were real, and they were incredibly small and negatively charged. The device consisted of a funnel-shaped cathode ray tube, as you can see here in this figure. The smaller end of the funnel-shaped tube has a cathode at the tip of the smaller end, as you can see here, and the anode inside of the smaller end. Both anode and cathode are each connected to a voltage source. The tube has a magnetic surround electrically charged positive and negative plates near to anode, and electron being passed through the plates in a widening evacuate tube. Some will be deflected and it goes to the upper and the low edge, while the others will be undeflected, going straight to the center of the tube. So here he outlined the follows, like positive and negative charge attract on one another, positive will repel one another, and negative charge repel one another, and the positive and negative charge of exactly the same magnitude sum to zero. For example, in this case, I have a positive 1 and negative 1, so the sum will be 0. So a few years later, Robert Millikan took the next step. He created a tiny oil droplet, charged them, and suspend them between two metal plates. By adjusting the electric field, he could make a droplet hover. A cylindrical container is divided in two sections, upper and lower section. The upper section has a positively charged plate at its base, and the base of the lower section is negatively charged plate. An atomizer is attached to the upper section from the outside of the cylindrical chamber. The atomizer has an outlet tube that sprays final oil here inside the upper section. And the lower section, a light source, as you can see here, eliminates ionizing radiation that enters the cylinder across from view microscope. So the oil droplet passing from the upper section to the lower section to the positively charged plate become charged oil droplets, and they're suspended over here in the electric field at the center of the lower section. From this, he could calculate the charge of each droplet. Every value that he found was a whole number multiple of a single, smallest charge. The charge was 1 electron. So the measured charge of one drop was always a whole number multiple of negative 1.60 times 10 to the negative 19, the fundamental charge of a single electron. So in this case, if I have, let me grab a pen over here and try to help you. So here, if I have negative 4.8 times 10 to negative 19, and I want to find the number of electrons, what I'm going to do will be, I will divide by 1.60 because I know that is the charge for 1 electron, and then I will divide both, so we're going to have 3 electrons over here. Okay, so we can deduce the mass of an electron. We can deduce the excess of electrons. In this case, I was deducing the excess of electrons over here. So was a very good discovery. After discovering electrons, Thomson proposed a model of the atom. He imagined electrons embedded in a positively charged sphere, like you can see here. So like a raisin in a plum pudding. It was a creative idea, but it didn't last long, because Ernest Rutherford tested Thomson's model by shooting positive charge alpha particles at a thin sheet of gold foil. Most particles passed straight through, but a few bounced back. This was shocking. So imagine it like you are holding a very thin paper and somebody come in the room and shoot you. But the bullet deviated. It's kind of, the bullet found some protection that deviate the way of the bullet. So in this experiment, positive charge of particles are directed from the source with the lead block at the ultra thin sheet of gold foil that you can see over here in the center. The sheet stands upright at the center of the detector, which forms a circular wall around over here. Form a circular wall around of the sheet with a gap across from the source. When the alpha particles hit the gold foil, a few are deflected through large angles back at the detector. Most alpha particles pass through with little or no deflection, like you can see. So Rutherford, using the plum pudding model, he predicted the result is that all alpha particles pass straight through electron interspersed with the sphere of positive charge. The actual result suggests a nuclear model with central nucleus comprising protons and neutrons, surrounded by electrical cloud. Alpha particles pass straight through the electron cloud but are deflected by the nucleus. So, through this experiment, Rutherford proposed three key ideas. Almost all the mass and all the positive charge of an atom are in the nucleus. Most of the atom's volume is empty space where electrons move. The number of electrons equals the number of protons, making the atom neutral. So Rutherford model explained a lot, but not everything. Atoms were heavier than expected. So later, James Shaddock discovered the missing piece, the neutron. So neutrons have mass similar to protons, but no charge. This explains why atoms of the same element could have different mass. So now we know atoms contain three main particles: protons, neutrons, electrons. So we know that protons and neutrons are heavy compared to electrons. And you can see over here the mass. The mass of electrons is very small, extremely light. So the charge of the proton and electron are equal in magnitude but opposite in sign. The neutron has no charge at all. So the identity of an atom comes from protons. So that is the identity of the atoms. This will never change. This number is called the atomic number. If an atom has 6 protons, we know that it's carbon. If it has 8, we know that it's oxygen. Change the number of protons and you change the element. So here we have, now you know that protons you can never change. You can change the number of electrons, you can change the number of neutrons, but no protons. Because protons is the number that defines the element, like your ID. So the most important thing in chemistry is the periodic table. Periodic table can talk to you, can explain to you everything. So if you have a periodic table as a friend, you can go very well in chemistry. So the periodic table has 7 rows in the main table and 2 additional rows excerpted from rows 6 and 7 sat below the main table. The table is comprised of boxes that represent each element, right? So in the table shows each box has the atomic number, and we have a chemical symbol, and also the name. For example, the element beryllium has atomic number 4 and a chemical symbol Be. The element thing has atomic number 50, and it's over here, right? Sn. So that is the chemical symbol. So if you thought that thing should be T, so it's better to take a look in the periodic table, because the names come from Greek words or Latin words, and you can make some confusions over here. Like silver will not be S, will be Ag. So practice that, okay? So each element is identified by a unique atomic number and with a unique chemical symbol, like carbon C, nitrogen N, helium is He. Let's test your understanding here. If you have your periodic table in your hand, which element contains 50 protons in its nucleus? Look at this. If you go here, thing, and that's 50 protons, is the same number of atomic number, so we can find that is thing. Okay? It's easy to find it, which one it is, by the atomic number, knowing that the protons is the equal atomic number. And of course, atoms of the same elements always have the same number of protons, but they can have different numbers of neutrons, as I said before. These versions are called isotopes. For example, neon can have 10, also 11 or 12 neutrons. They behave the same chemically, but they have a different mass. This we call isotopes. So the relative amount of each different isotopes naturally occurring sample of a given element is roof constant. This percentage are called the natural abundance of the isotope. So when you talk about an element, like here, we have neon 20, neon 21, neon 22. That is the mass number, and that is important to know how you represent. The mass number will be in the top in the left side, atomic number down in the left side, and then we have the chemical symbol. Knowing that the atomic mass, the mass number, is represented by A and is the sum of protons and neutrons will help you a lot. And probably you're asking me why we don't add the electrons, because electron is very, very light, as you could see before, and it's like if you go to the doctor and you go to the balance and you want to weigh like your real weight, so you are complete without clothes anything, and then you forgot to take out your ring, and then it's like, oh, please wait a little minute because I forgot to take out my ring. That doesn't make sense, because the ring will not add any special weight in your whole body, right? So that the same thing here. So electron will not add anything like that will change significantly the mass. So this is why the mass is just the number of protons and number of neutrons. So when you represent the isotope, normally we use the chemical symbol and the mass number. Like here, I have a neon 20 or neon 21 or neon 22. So when you look to the number of protons, it's always the same. What's varying here is the number of neutrons. Of course, the number of mass will change. And here we have the natural abundance over here. So most of the neon that you're going to find will be neon 20, 90% of that. Only 0.27% will be neon 21, and 9.25% will be neon 22. So let's test your understand over here. An argon isotope has a mass number 40. How many neutrons does it contain? So you know that argon, we have 40 as a mass, and you can look at the periodic table and you're going to see the atomic number, which is 18. So if you grab, and if you know the mass is protons per neutrons, you can have 40, which is the mass, minus 18, which is the protons. That is the same number, the same of the atomic number. We're gonna have 22. Pretty easy, right? Just pay attention. So let's test again. Carbon has two naturally occurring isotopes, C12 and C13. If circles represent protons and squares represent neutrons, which image best represents the C13 isotopes? Think well. Stop your video and try by yourself. So the first thing that you need to remember here is the protons will never change. What is changed is neutrons. So a carbon, if you go to the periodic table, you're going to see the carbon has 6 as atomic number. So that means I have 6 protons. This will never change. So here it says that circle represents protons, right? So we have 1, 2, 3, 4, 5, 6. That's good. 1, 2, 3, 4, 5, 6, 7 cannot be this. Here we have 6, but let's count how many I have in the total. So I must have 13. So I have 6 here, 7, 8, 9, 10, 11, 12, 13. And here I have 6 protons, and then 7, 8, 9, 10, 11, 12. So cannot be here because it's only 12, so this is the right answer. So ions is an element that lost or gained electrons. So we have positive charge ions such as sodium, which are called cations, and the negative charge ions such as fluorine or fluoride that are called anions. So, and when you have negative charge, means that you gain, the element gain electrons. Okay, so if I know that oxygen has only 8 protons, I know in a neutral element I will have 8 electrons. However, this ion over here gain 2, so that means I need to add 2 electrons over here, and I'm gonna end with 10. Good? So let's practice a little bit more. So here I have cadmium. Oh, can you see here 95? That's the mass, right? This is the symbol, that is the mass, and we have the atomic number, which is the proton. So if I need to figure out this, so I'm gonna start with the protons over here, because that will never change, right? So it's 48. Then I know the mass, which is 95. So now I want the number of neutrons, which has 0 charge. This is why it's 0. That doesn't mean number is 0, okay? Neutral. So how I'm going to calculate this will be the mass. Oh, so atomic number is the same of the protons, right? So it will be the mass minus the protons. So remember, protons plus neutrons, so we're going to have 47. Electrons, since I have no charge over here, is the same number of protons. Okay? So, and here I only have the mass, but I know from the periodic table the atomic number. So the mass is 28, but in the periodic table, I know the aluminum has 13 protons. And I know that it's 28 grams per mole of the mass and 13 atomic number. Okay, so but look at this. I have a 3 plus, so that means lost electrons. This element lost electrons. So to calculate electrons, I will reduce 3. So I have 10 electrons, but number of neutrons is 28 minus 13, number of protons, not electrons. Okay, so I have 15 over here. And this element over here, see, I have a charge as well. So if I have a charge, this is -2 gain electrons, right? So I have the atomic number which is the same of the protons, and they have mass. So I can fill it out that. So now I need to know the electrons. So electrons will be 8 plus 2, because I got 2, so 10. And number of neutrons will be 17 minus 8, so I have a 9. Good? Great. One more. In light of the nuclear model of atom, which statement is true? For a given element, the size of an isotope with more neutrons is larger than one of fewer neutrons? Or for a given element, the size of an atom is the same for all of the element's isotope? It's B. You're right if you answer B. So the size will not change. What changes is the mass. Okay? So the periodic table organizes elements by increasing atomic number and groups then by similar properties. Metals, nonmetals, metalloids each have a characteristic behavior. Groups, vertical columns, often share chemical patterns. So the periodic law, elements with similar properties record an irregular pattern. When arranged in order of increasing mass, elements with atomic number 1 through 20 are arranged in a row. You can see over here 1 to 20. The following list provides the atomic number and element symbol and element's highlights for sharing similar properties. If you go to this column over here, all those elements has the same type of properties. They all have just one valence electrons. And if you don't know what is valence electron goes for, we're gonna talk this a little bit later. But all those elements over here tend to lose one electron. If you go to this group over here, group 2, they all tend to lose 2 electrons. If you go to those over here, they are very reactive and they all tend to gain 1 electron and go on. So Mendeleev's table contains some gaps, which allowed him to predict the existence of yet undiscovered elements. This is what makes Mendeleev so special. And in the modern table, elements are listed in order to increasing atomic number harder than increasing relative mass. So that is important, okay, because it can ask you a question and a test. The modern periodic table also contains more elements than Mendeleev's original table because more have been discovered since that time. This is why I love Mendeleev. Of course, he was not the only one scientist working the periodic table. And I don't love him just because he invented the vodka. I love him because he was so smart and left a gap to with the providing the characteristics and properties to the undiscovered elements. He's always like, okay, I don't know which elements this one, but it will have this property and it will be discovered one day. So we're gonna leave this space empty over here. This is how smart he was. So that is the modern periodic table. So you have they are divided in groups and periods, right? So there are 1 to 18 over here. The metalloids separate metals on the left from non-metals on the right, with the exception of the non-metals hydrogen on the upper left side over here. Okay, chemical symbols for the metalloids are follow like bottom over here, Si, As, Ce, like tellurium. All those elements are metalloids, so they have both characteristics of metals and non-metals. Okay, so we have non-metals like carbon, sulfur, bromine, iodine, all those over here. Okay, so elements in the periodic table are classified as the metals, non-metals, and metalloids. We know the metals had the on the lower left side and the middle of the periodic table. So all this over here are metals. Okay, so Good conductors of heat and electricity can be found in the flat sheets because they have malleability, can be drawn in wires because they are ductility, often shine, tend to lose electrons when they undergo chemical change, like all the group 1 has tend to lose 1, all group 2 tend to lose 2 electrons. Chromium, copper, strontium, and lead are typical metals. Non-metals lie in the upper right side of the periodic table. So if you have a periodic table over here, all these over here are non-metals. And one is a liquid at room temperature, like it's bromine. The most of them are solid at the room temperature, like carbon, phosphorus, sulfur, selenium, iodine. 11 are gases at room temperature, like hydrogen, helium, nitrogen, oxygen, fluorine, neon. Oh yeah, I forgot to highlight the hydrogen over here. So that is no matter. So as a whole tend to have these properties: poor conductor of heat and electricity, no ductile, and no malleable. They gain electrons when they undergo chemical change. And if you go to group 17, group 16, group 15, they all tend to lose 1, negative, 2, and 3 electrons. Okay. So metalloids are sometimes called semimetals. They lie along the zigzag diagonal line that divide metals and non-metals. They exhibit mixed properties. That's why they call semimetals or metalloids. Several metalloids are also classified as semiconductors because they are intermediate, high temperature dependent electrical conductivity. So in the periodic table we have the main group elements whose properties tend to be largely predictable based on their position on the periodic table. And transitional elements or transitional metals whose properties tend to be less predictable based simply on their position in the periodic table. So here we have the main group of elements, like group 1 and 2, and the metals. Okay, they have a fixed charge, so it will be plus 1 and plus 2 because they tend to lose 1 electron in group 1, 2 electrons in group 2, and this all has to do with the valence electrons that we're going to talk later. And here we have the main groups in the side containing metalloids and also non-metals and some metals over here. They are fixed charge and they are more predictable. So each vertical column is called group or family, and each horizontal row is called a period. So if you have your periodic table over here, we're gonna have the groups and the vertical and the periods and the horizontal form. Okay, so the groups are number 1 to 18, and all the periodic tables they use A and B groupings. Periodic table, the main groups elements are in column label with the number A, 1A to 8A, or group 1 to 13 to 18. Like I said, those are the main groups over here. Those over here and those over here. Okay. So noble gas, one of the most important groups here because they are noble, because they have low reactivity. They are very stable. They don't tend to react. So the most familiar noble gas is probably helium, used in a few balloons. They are chemically stable, doesn't combine with the other elements to form compounds. So this is why we use in balloon. They are safe because they don't react. Other noble gas like a neon, often used in electronic signs, or argon, small components of our atmosphere, or krypton and xenon. And we have alkali metals. Group 1. The group 1, they are very reactive metals. They only have 1 valence electrons. They need to lose that electrons, really crazy to lose, because all the atoms look for stability. Exactly like us, we look for stability. So we fight for that. This is why we study, this is why we fight for finding good jobs. So they look for stability. If they lose one electron, they will be more stable. So when they are by itself, they are very unstable, very reactive. Here we have a sodium. If you add the sodium and water, you're gonna see fire. You're gonna see sparkly. The small piece of sodium will like jump as crazy on the water because they are very reactive. So they will explode violently. So lithium, potassium, and rubidium are also alkali metals. Then we have in the second group the alkaline or metals. They are reactive, but not as much as the alkali metals in the first group. Like calcium, it reacts very vigorously with water, but doesn't explode dramatically like sodium. Okay, so they tend, this is in the group 2, so this group over here, so group 2, they are very reactive, not as much as the group 1. Okay, so alkaline or metals. So we have calcium, we have magnesium, strontium, barium, all those. Halogens, a very important group over here, group 17 or group 7A. Okay, so are very reactive non-metals. They only need one electron to be stable. They have 7 valence electrons. We're gonna talk again. We're gonna talk about the valence electrons later. Okay, valence electrons. So fluorine, chlorine, bromine, all those elements are very reactive nonmetals. Let's test your understanding. Which term best applied to lead? Transitional element, metal, main group element, non-metal, halogen, non-metal, or main group element, metal. Let's look at the periodic table. Here we have lead over here. So remember, this here are main groups, and those over here are the main group, right? So we know that lead is in the main group, but it's a metal or no metal. So this part here is still metal, and this is metalloids, and this is no metals, right? So main group element, metal. Good. So ions and periodic table. A main group metals tends to lose one electron, forming a cation with the same number of electrons as the nearest noble gas. So, and the non-metals tends to gain electrons. Not gain, tend to gain electrons, and I put over here to gain electrons. So they tend to gain electrons. Okay. So ions, the group 1, they will form ions like positive charge. For group 1 would be 1. So in the general, have a tendency to lose one electron, form 1 plus ions. In the second group, tend to lose 2 electrons and form 2 plus ions. The halogens tend to gain 1 electron, form anions. So we have -1. Oh, that's here is -2, and here is -1. Okay, so group over here. Oh, sorry. Group 2. So those will tend to gain 2 electrons, and this will tend to gain 1 electron. So this is a form -1 ions, -2 ions. So for the main group elements that form cations with predictable charge, the charge is equal to the group number. Remember, so group 1 will be +1. Group 2 will be +2. For main groups, elements that form anions with predictable charge is equal to the group. So if you go 17, 16, okay, so forget about the 10s over here, because in the past we use 7 and 8. So now 17 will be 7 valence electrons. So will be the group like 18, noble gas, -17, so -1. 16, -2. Why? Because they have 7 valence electrons here, and they only need 1 to be exactly behave exactly like a noble gas, which has 8 valence electrons. Okay, so 18 minus 17 is negative 1, 16 minus 18 will be negative 2, and so on. Transitional elements may form various different ions. So we have fixed charge for the main elements, and transitional metals we have variable charges. And just to call your attention over here, metals will form positive ions, so we have cations, right? So, and then if you have to write the name over here for the metals, like this magnesium ion, so we're gonna write magnesium ion. We have a lithium, will be lithium ion. But in case of the metals that don't have fixed charge, most of the transitional metals, we're gonna write the name, the charge in the Roman number plus the ion, like over here, iron. So we have a charge 3, so it will be iron 3 ion. And then we have cobalt 2 ion. So we call this Stokes system, and you need to indicate the charge on those cases. Okay. Atomic mass is sometimes called atomic weight or standard atomic weight. Most of the elements, as we could see before when they talk about isotopes, they exist as a mixture of isotopes. I said, like we saw before, because probably most of you already have chemistry before, or at least have a contact with chemistry in the high school. So probably you have learned about isotopes. So most of elements exist as a mixture of isotopes. So the atomic mass on the periodic table is weight average of a naturally occurring isotopes. For example, chlorine atomic mass reflects both chlorine 35 and chlorine 36. So let's go to this example, neon over here. So we have a neon 20, neon 21, neon 22. So see the percentage over here, they vary. 90% of neon that you're gonna find in nature will be neon 20. So, and if you look to the number of protons, they have a fixed number of protons. Remember, that is the identity of the element, so it will never change. But the number of neutrons are the ones that are changed, so the mass will change, because we know the mass is protons plus neutrons. Okay, so we can solve a problem over here. So naturally occurring chlorine consists in 75.77% of 35, and we have the chlorine 37 over here. I said a few slides ago 36. It's chlorine 37, I'm sorry. And we have only 24.23% of this. I know the final mass must be close to 35, right? More than 37, because I have more 35 than 37. So in order to calculate this, I'm gonna use the percentage times the mass of each one and then add it together. So my final mass, the average, will be 35.55. You can never do this, 35 plus 37 divided by 2. This is a regular average mass. So this is not what you're going to do. You're going to do exactly what you do if a grade, for example, if I say that to you 60% is exam and 40% assignment. You know, even if you get like 100% in your exam, you're going to multiply by 60%. And then if you have 0 on your assignment, imagine times 40%, your final grade would be 60, right? Doesn't matter if you got 100. So the same thing with atomic mass here. You need to take in consideration the abundance of each one. So we're gonna use the fraction of the isotope times the mass of isotope. In this case, the fraction will be the percentage divided by 100. So this is why if you get 60%, it's 0.6, and so on. So let's recall and see your knowledge over here. So without doing any calculation over here, okay? So we have here carbon 12, natural abundance is 98.93%, mass is 12, and carbon 13, natural abundance is 1.07%, mass is 13.0034. Without doing any calculation, determine which mass is close to the atomic mass of carbon. Look, if 98.93%, almost 99%, has a mass of 12, and just 1% has a mass of 13, of course, my final mass will be close to 12, right? No calculations needed. So, a sample of a compound or an element injected in the mass spectrometer. A mass spectrometer is a V-shaped tube. A pair of magnets is kept inside. The tube as at its vertex. A heater vaporizes the sample and electron beams ionize the sample. A beam of charged particles pass to two electricals over here. Fields accelerate the particles. And an angle inside of the tube, you can see here, the beam of charged particles pass through two magnets, one above and one below. The magnetic field separates the particles. The beam split into sections, so it's approach a detector at the end of the tube. The lightest particle hit the detector near to the edge, and the heaviest will hit on the lowest part. An electrical signal is produced when the ions strike the detector. So this is how a spectrometer mass work. So that's it. That's all. Bye for now.